Hi everyone, in this video we're going to demonstrate a fundamental property of vector spaces. That if we consider a base of a vector space, then all the vectors in it can be uniquely expressed as a linear combination of the base. Let's discover the maths. First, remember that a base of a vector space V is a set of linearly independent vectors that is a generator system of V. So, the result we want to demonstrate is the following. If V is a vector space over a field K and B equal to the set E1, E2 all the way up to En is a basis of V, then every vector of V can be uniquely expressed as a linear combination of B. To begin with, since B is a basis of V, in particular it's a generator system of V, therefore every vector can be expressed as a linear combination of B. So we already have the first part. Now we'll show that this expression is unique. To do this, suppose that small v is a vector of big V, and we're going to suppose that this vector has in principle two expressions as a linear combination of V. Small v equals alpha 1 E1 plus alpha 2 E2 all the way up to alpha n En, and v equals beta 1 E1 plus beta 2 E2 all the way up to beta n En for certain scalars alpha I and beta I. And since our goal is to prove that this expression is unique, let's show that these two expressions are actually the same. To do this, note that the vector 0 is clearly V minus V. Now the key is to replace each of these V's with one of the previous expressions. So for the first V, we write alpha 1 E1 plus alpha 2 E2 all the way up to alpha n En minus the second V, beta 1 E1 plus beta 2 E2 all the way up to beta n En. Now we remove the parentheses so that in the second expression we change the sign of each of the terms. So we have alpha 1 E1 plus alpha 2 E2 plus all the way up to alpha n En minus beta 1 E1 minus beta 2 E2 minus all the way up to beta n En. Now we take out a common factor of the EI's, which we can do because it follows from an axiom of the definition of vector space, and we obtain alpha 1 minus beta 1 times E1 plus alpha 2 minus beta 2 E2 plus all the way up to alpha n minus beta n En. Notice that we've obtained a linear combination of vectors of B equal to 0. And since B is a base of V, its vectors are linearly independent, so the scalars are 0. And we have alpha 1 minus beta 1 equals 0, alpha 2 minus beta 2 equals 0, and all the way up to alpha n minus beta n equals 0, from which alpha 1 equals beta 1, alpha 2 equals beta 2, and so on, up to alpha n equals beta n. Thus we've shown that the alpha i's are equal to the beta i's, and so it follows that the previous expressions are the same. We've shown that the expression as a linear combination of a vector V with respect to a base is unique. And if this expression is V equals alpha 1 E1 plus alpha 2 E2 and so on up to alpha n En, we say that alpha 1, alpha 2 up to alpha n are the coordinates of V with respect to the basis B, which as we know determine the vector. So we write V equals alpha 1, alpha 2 up to alpha n B. I hope you found this useful. Don't forget to subscribe if you haven't already, and I'll see you again very soon to discover more maths.